Hello, and welcome to part 1 of the course overview module. In this part of the module, we're going to be exploring the motivations for and challenges of concurrent and network software. Concurrent software can simultaneously run multiple computations that potentially interact with each other. Network software defines protocols that enable computing devices to exchange messages and perform services remotely. We're going to start by talking about some of the motivations for concurrent software. Obviously, these days, some of the key motivations are to leverage advances in hardware and software. For example, it's almost become the case that these days it's hard to buy a single-core CPU. My cell phone, my laptop are both quad-core processors. I regularly use desktops and servers with 8 cores, and there are many more cores on the way. Moreover, operating systems like Unix and Linux, Windows, VxWorks, and so on take very good advantage of these multiple cores. Even middleware, Android, Java virtual machines, Corba, DDS, .NET also take advantage of the multiple cores. So the main motivation here is to take advantage of these cores and use them effectively to improve various aspects of your software. One thing that can be improved with all the advances in hardware and software is the way in which we structure our concurrent programs. Historically, when people built software, they had a tendency to write event-driven code. For example, back in the days of early versions of Windows and early versions of Unix interfaces, the software was typically organized using an event loop or event-driven model, where you had one thread of control that would do all the processing. It would handle user interface events, it would talk to files, it would make communications across the network, and so on. And it turns out to be very difficult to program this software, to structure it properly. Because anytime you run into a situation where you might block, you have to handle events and do everything using some kind of message queue and event loop, which is tough to program and difficult to optimize. Nowadays, with better support for concurrency in the operating systems, the middleware, and the hardware, we have a more effective way of being able to structure the software. For example, on modern user interfaces in environments like Android and iOS and other user interface environments, you can have multiple threads in the background that do long-running computations that can afford to block, which allows you to be able to structure the software in a more natural way. Here's an example of this, using a little snippet of code from a running example we'll talk about many times throughout this course that occurs in the context of the Android environment. In this particular example, we have a so-called click listener, which handles button clicks from the multi-touch user interface. When someone clicks a button, this code launches a thread. It starts up a thread of control to run in the background. And this thread will download an image from a remote server across the network, and then be able to do some processing and eventually display that image back in the main thread of control. And if you look carefully at the code snippet here, you'll see that it has good cohesion between the various parts. The parts that are doing the processing are nicely cohesive in time and space, as opposed to being scattered all throughout the code in time and space, as would have been the case in previous environments where everything was driven by events. Once we've got better hardware and software support, we can also start to take advantage to improve performance, which is one of the main drivers for using concurrency in the first place. For example, in modern multi-core environments, we can parallelize the computations and communication that are taking place. We can overlap communication and computation and make it be able to take full advantage of the hardware to make things run faster on the different cores. Even in environments where we may not have access to multiple cores, you may have a single core machine, or you may have other constraints that make it difficult to be able to take full advantage of parallelism, it's still possible to use concurrency and multi-threading to improve perceived response time. For example, you can have your user interface thread blocking, being able to interact responsively to gestures and input from users, while still doing other long-running tasks in separate threads in the background, accessing the file system, accessing the network, and so on and so forth. There are also some complexities and challenges associated with concurrent software that's important to understand. Some of the complexities are called accidental complexities. These complexities arise from limitations with the tools and the techniques and the methods that we commonly use to build software. In some sense, these are self-inflicted wounds because we don't always have to do it this way. It's just conventional wisdom or common practice. One of the common problems that we have in the context of concurrent software is the traditional use of low-level application programming interfaces, or APIs, which are very tedious and error-prone and non-portable to try to use to write concurrent software. As a simple example, consider the use of the pthreads concurrency API that's available in many different versions of Unix. In this environment, you have a number of challenges. First, you tend to use low-level and error-prone data types, things like pointers to functions, to pass when you spawn a pthread. Likewise, you end up using various kinds of typecasting operations to cast some data to a void star to pass it when a thread is created, as well as to cast the void star back to whatever data structure you have internally that you're using to pass between the caller and the callee in the thread environment. The minute you start using cast, it turns off compiler type checking, which means that all kinds of subtle errors can creep into your software. Another problem is we have quasi-typed thread handles, which are easy to mistake and pass the wrong type in, and the compiler really can't give you effective type checking and error warnings and so on in your code. And of course, the fact that we're using pthreads is a dead giveaway that this software will not be portable to non-POSIX platforms. Lest you think we're picking on pthreads, be aware that almost all operating systems today that have C interfaces have these kinds of problems with the low-level APIs used for concurrency. Some other problems we have deal with limitations in our debugging environments and our debugging tools. A well-written, properly functioning concurrent program is a thing of beauty. But what happens when something goes wrong? How are you able to drill down, to look inside of your software, to figure out what's happening and how to take remedial action correctly? Well, there's a number of problems here. One of the problems we historically run into is that debuggers and the experience you get while debugging doesn't necessarily reflect the actual production software experience. For example, you may be single-stepping through some code in one thread while other threads are running, and the execution sequence and the execution times may not be the same as if you were running outside the context of the debugger, which makes certain kinds of timing properties and other kinds of scheduling and synchronization hazards difficult to identify and rectify. Another related problem has to do with race conditions, which are situations where multiple threads of control are simultaneously accessing unprotected data structures, corrupting them, crashing into various pieces, and otherwise potentially having mistakes that are very difficult to show until your program is in the most important situation while it's running in a production environment. And most debuggers don't support very good support for catching these kinds of race conditions in your development environment. In order to be able to handle these problems, you need to use more advanced tools, various tools like dynamic instrumentation or static analysis. And the links at the bottom of this page give you some pointers to more information where you can learn about some of these various techniques and tools. There are also some so-called inherent complexities associated with concurrent software. Inherent complexities arise from fundamental challenges in a domain. This is the rocket science of concurrent software, the things that require deep thinking and deep analysis to get right. Some of the common inherent complexities of concurrency and concurrent software relate to synchronization and scheduling, which deal with the order in which operations are performed or the time at which they are performed. And getting this right is tricky because there's so many states to manage in these large-scale, complex concurrent systems that it's difficult to keep track of them all and be able to assure that your software is actually going to do the right thing under the right circumstances or the wrong circumstances. Another problem that you have to wrestle with that's inherently complex has to do with deadlock, which are situations where threads end up having circular waiting dependencies on different resources. This example here illustrates a situation where thread 1 owns lock 1 and is trying to access lock 2, while thread T2 owns lock L2 and is trying to access and acquire lock 1. This is a good example of circular wait. Identifying, detecting, removing deadlocks is also an inherently complex aspect of trying to build concurrent software. If you take a look at this URL at the bottom of the page, you get a chance to see a bit more discussion of various challenges with developing concurrent software and some tips and ideas on how to apply various techniques to make those problems easier to wrestle with. Let's now talk about motivations for networked software. Well, one of the main motivations these days for network software has to do with enhancing collaboration and commerce. When I take my laptops or my phone or my desktop and I want to be able to share information between those different devices, I use networked file sharing software to make that easier to do. I communicate and interact with my friends and family by the use of social networking. When I want to go out and buy various books and other interesting things on the internet, I use various types of e-commerce support and online network transaction processing in order to be able to do those purchases in a safe and efficient way. When the universities and companies I work for need to be able to go out and get software or hardware, they use various business-to-business supply chain management and inventory control systems, which are also networked to be able to check to make sure that the people making the requests and the people who are honoring the requests are valid and certified and so on. Another motivation for network software has to do with scalability. Even though we've managed to add a lot of cores to a chip, there really is a limitation ultimately to how many cores you can run on a chip, at least at this point in the technology life cycle. In contrast, when you start networking together many computers, you can access a virtually unlimited number of cores and processors, as we're seeing today with large-scale data centers and cloud computing environments, where it's possible to lease or rent the cores, so you don't have to be responsible for the cost or maintenance effort required to own and sustain these technologies over the life cycle. If you only have one computer or one core and something goes wrong, then you're probably just out of luck. In contrast, one of the other motivations for network software is to be able to minimize these single points of failure through the use of replication in order to make the software more available. Replication allows you to have many different versions running on different parts of the system. So if something goes wrong someplace, if it hangs or crashes or is compromised in some way, then you can fail over rapidly in order to be able to keep the computations occurring and not degrade user experience or be able to disrupt the commerce or mission critical nature of the systems that you're implementing. Yet another motivation for network software is the ability to reduce cost through sharing. For example, once you have a network, it's not required to have a separate file system for every machine, or a separate backup system for every machine, or a separate printer for every machine or device. Instead, you can amortize those investments over a work group so that the overall costs are reduced and you're more able to effectively share and use perhaps more powerful or more precise equipment in order to carry out your work as a member of a team or a group. There also, of course, are challenges with network software, just like there were with concurrent software. One of the most fundamental challenges that we've been working and wrestling with for decades is the prevalence of the use of so-called algorithmic decomposition to develop the networking portion of the software. This is one of the key accidental complexities. If you take a look at a lot of the classic literature for how to program network applications and software, you'll find that even though this literature does a great job explaining how sockets work or other mechanisms for doing inter-process communication, most of the examples tend to be written using so-called algorithmic decomposition, also known as functional decomposition, which is done by doing a top-down decomposition with stepwise refinement of the algorithmic steps that you're trying to carry out. And while these approaches may work for very small learning exercises or very small programs, if you start using algorithmic design too broadly throughout your software, you end up programming yourself into a corner, which makes it very difficult to change the way your system behaves to meet new requirements or to be able to execute efficiently in new operating environments. Another problem that we run into a lot in networking has to do with the tendency of many people and groups to continually rediscover and reinvent core network software components. I can't tell you the number of times I've worked on projects throughout my career where people on the teams I was involved with thought it would be a great idea to reinvent many different layers of middleware, to build those things in-house. And while that can be tempting and fun, the consequences with respect to quality assurance and sustainment over the life cycle are very problematic. most organizations simply don't have enough in-house expertise to build these kinds of complex distributed computing and network computing infrastructure capabilities anymore. And even if they have those people in-house, it's not necessarily clear that those people will be there for the long term. And yet this is a common problem we see a lot in the industry. In fact, this is so common that my colleague and friend Steve Inyosky has actually written a paper talking about what he terms middleware dark matter, which gives a name for this phenomena of people's tendency to reinvent the networking software infrastructure time and time again. There are also, of course, a number of inherent complexities in the space of network software. One of the classic problems you see when you move from a standalone way of doing things to a networked way of doing things is that issues like latency, which is delay, and jitter, which is variation in the delay, become much more problematic. If you're building software that runs in a single address space on a single machine, latency and jitter are relatively easy to deal with, especially if you have a good operating system that gives you strong control over scheduling priorities and being able to avoid the hazards of real-time processing, such as priority inversions and so on. When you start connecting things together through networks, even if the networks are fairly efficient and high speed, there are inevitably delays that occur because of the different layers of software between the sender and the receiver of a message. Moreover, these delays also tend to vary depending on the amount of congestion that's occurring or the amount of traffic that's flowing and the contention on a network or a shared network. In those environments, you'll have a very difficult time being able to get predictable performance, which means you can't use network software for certain kinds of mission-critical applications. Another problem that you run into frequently has to do with reliability. When I was a graduate student, first doing research in middleware back in the early 90s, we used to joke and say that a network system was one where a file server you never heard of before would cause your workstation to hang. Well, mercifully, things have got a lot better over the years, and that kind of infrastructure is much more reliable. But it's still the case when you build network systems, you have to be very careful about the reliability aspects. This is particularly tricky because of a force called partial failure, which arises frequently when you start splitting your system up into many different parts that run in different computers connected in a network. Partial failure is something that occurs when one piece stops working and other parts are still running. One of the tricky parts, because of the issues of latency and jitter, is to try to figure out whether something isn't responding because it's crashed, it's hung, or it's simply slow to respond because it's busy. And trying to figure out the protocols and services and support infrastructure to deal with partial failure is very tricky. One of the main issues that's driving people's awareness of networking these days, of course, is in the realm of security. Every day you learn about problems dealing with cybercrime, espionage, identity theft, situations where people kidnap data and hold it hostage for ransom. As we were getting ready to film this particular module, there had been a warning issued by the Department of Homeland Security advising people to turn off Java in their browsers because of the perceived or real threat of people being able to compromise, bad people being able to compromise their machines. So these are very problematic issues, they're pervasive issues, and one of the challenges we have is a lot of the legacy software that was developed wasn't really meant to run in a overly connected, inter-networked environment. And so as a result, people tend to use low-level languages, they tend not to check for various defects like buffer overflow, and so security is a never-ending problem in this space. There's a paper at my website that goes into a bit more detail talking about some of the inherent and accidental complexities of network software that you might want to take a look at for additional information. So to summarize this part of the module, concurrent and network software helps with several things. First, it helps to be more effective at leveraging these advances in hardware and software that we've become accustomed to because of Moore's law and other ways in which commoditized software gets better, faster, cheaper at a regular pace. But it also helps with other areas as well. It helps to meet the quality and performance needs of applications and services that go above and beyond what the hardware and infrastructure software is going to be able to do. This allows us to be able to get better fault tolerance, better real-time behavior, better security, and so on. Keep in mind, however, that there are inherent and accidental complexities that make concurrent and network software difficult. Some of these issues arise from self-inflicted wounds, from limitations with the use of low-level APIs or algorithmic decomposition, and so on. Others arise from fundamental challenges in particular domains, the really hard problems, the ones where you have to think deeply, where it helps to have a good theoretical background, where you can leverage other people's experience to try to avoid reinventing the wheel time and time and again to solve hard problems that already have been solved by others before you. Well, clearly, as concurrent and network software systems become more pervasive, as they grow in scale, as they have additional functionality, as we begin to rely on them for more and more of the mission-critical and common everyday infrastructure we take for granted, things like commerce or homeland security or civil aviation and transportation, it's important to figure out how to be able to cope with these hard problems, to be able to figure out how to deal with the difficult challenges and be able to resolve them so you're in a better position to be able to slay the demons and dragons of complexity. In our next section, we'll start to discuss some techniques that you can apply that we'll cover throughout the rest of this course for how to address these inherent and accidental complexities.